is make sure that when you convert the objective function over, you've got to bring the 4x1 over and the 6x1 over. So the coefficients on the x1 term there is going to be negative on both of the variables there. And then you're going to get equal 0. So it's always going to be the case that when you start these problems off, the p, the objective function, is going to have 0 for the right-hand side. And then you're going to have negatives here underneath the x's, all negatives usually, especially for the maximum problems where they're required to be positive coefficients generally on these, particularly these. So these are going to be negatives. For the tableaus, I think I've been switching these, but I think these are the non-basic variables, but the way we find them is the same way. So there's no really doing this one down here until you do this. So if you don't know how to do this, then you're not going to be able to find the solutions. I think 2 of the 3 groups got this. But again, you go over, find the 1 with zeros everywhere else, and then you would label this row x3, and its value would be all the way over here, 5. So x3 is 5. x2 is the non-basic variable here. It's got 1 and zeros everywhere else. The column where you see the 1 and everything else is x2, so x2 is equal to 15. And then the basic, or the non-basic variable here is s3, so its value is 12, and p is equal to 45. And then everything else, all the other variables that don't have one, you have 4 here, you've got 7 total, so the other 3 must be zeros. Here you have 4 non-basic variables, and that leaves 2 basic variables, and the basic variables always take on the value 0. And the non-basic variable values will always be in the right-hand side, 2, 3, 11, 18, 2, 3, 11, 18, not necessarily in the same order. And here's the graph that you would graph for number 3. It's a bounded feasible region here. Graph the 2 inequalities, everything points down. 0, 0 is a solution, as will be the case. And I didn't check 0, 0, but it's also a corner point. So we have 4 corner points here. All right, now when you do the simplex method, you should find the same thing, that the max is 80, and it occurs when x1 equals 4 and x2 equals 2. All right, any questions on any of the rest of this on here? I'll do the matrix version. I saw one correct solution there, but I didn't see any of the work, so it may have been on the graph, it may have been the matrix method. You have any questions on these problems? Okay, well, hearing none, seeing none in the chat, then what we'll do is we'll go on to the next section. Turns out that solving maximum and minimum problems, maximum problems are much harder, or much easier. The problems we're going to do today are a little bit harder because you interpret the Tableau in a different way. And there's a couple of things you have to do in order to, that you have to do in addition to what you would do in the maximum problem. And the big theorem we're going to use here is this fundamental principle of duality. We now know how to solve a maximum problem. What this theorem is saying is that if you can set up this parallel problem called the dual, D-U-A-L, if you set up the dual problem to a minimum problem, the solution to the minimum problem will be the solution to the dual maximum problem. So what we're going to do is we're going to start with a problem in standard form for minimum problems in linear programming. We're going to change it to its dual. Its dual will be a maximum problem. We'll solve that maximum problem by entering in initial simplex tableau and then putting it through the simplex program on the calculator and getting the final simplex tableau. And then we'll have to interpret the final simplex tableau in a slightly different way in order to find the solution to the original minimum problem. So these problems are long, and so I want to show you the couple of steps that you're going to do in addition to what we normally would do. And so here's a set of notes. I'm not going to go through this much. You can read those. But part of it involves writing the transpose of a matrix. So this is another matrix operation. And you can see that it even appears on the calculator because it's used in a lot of different contexts. So for example, if you go to the matrix menu in the math menu, you see this little t. It looks like a superscript t. This is the transpose. And all it does is it takes an original matrix, and if you transpose it, it switches the rows to columns and the columns to rows. So in number one, if you take I'm just going to write it this way. Here's the original matrix, and you take the transpose, then you're going to rewrite this matrix, and the first row becomes the first column. The second row becomes the second column. This is just a mathematical function, and this is the first step that we need to do in order to write the dual. In a problem like 6, if this matrix is 2 by 4, then the transpose will just flip those numbers and be a 4 by 2. So you would take the first row, 7, 3, -1, 3, and it becomes the first column in the transpose. Take the second row, and you get this. So this here is the transpose of this matrix. Okay, so why don't you try number 7. And write in the chat the third row of your matrix. So write the whole transpose matrix from number 7. And then just in the chat, so I know that you're picking this up, write the third row of the transpose matrix. If you don't know, just throw a question mark in there. Okay, good. So the third column of the original matrix will be the third row of the transpose. So yeah, here it is, -1, -7, 1, and 3. All right, so that's going to be a step that that happens. All right, so let me tell you where you get this first matrix, and we'll go through the steps. And I guess it's kind of 2 steps here, but if you're looking at this after class, here's what you want to do. And I'm going to just say this, and then we're going to go do it. You start with a minimum problem. And the difference between a minimum problem and a maximum problem is that the maximum problems typically have all less than or equal to a positive number. For minimization problems, most of the constraints will have greater than or equal to some number. Use the coefficients and constants in the problem constraints and the objective functions to form a matrix. So the matrix that you're going to form, that you're then going to transpose, is made up of the coefficients of the original problem. So here's how I would recommend that you go ahead and do that. So we're looking at problem number 10 now. I'm going to call this the matrix of coefficients. Notice that we have an x1, we have an x2, no other x's, but then we have this variable c. Now, we usually write c. I guess I'm not going to put c here. I'm going to put right-hand side instead. Now, you're going to list your constraints first, and then the objective function last. There's only going to be one objective function. So if we start with this inequality, notice that they're both greater than. We're going to write the coefficient of x1, the coefficient of x2, and then the right-hand side. So we're going to form a matrix of coefficients from the constraints and the objective function. Continuing, we have 3x1 plus 1x2, and then on the right-hand side would be 9. We're going to ignore the basic constraints, or what we call those the non-negative constraints in this book. And we're going to go back up into the coefficients of the objective function. 12 and 5, and we're always going to start with 0 here. Okay, so here is the matrix of coefficients from the original minimum problem. Something x1, something x2, and then we've got the right-hand side. Okay, the next thing we're going to do is then take the transpose of this matrix. So just as you did in that first set of exercises, the first row becomes the first column, second row becomes the second column, third row becomes the third. Now, because we've transposed the matrix of coefficients, we're no longer dealing with the same variables. We need to write a new system or a new linear programming problem. So what we're going to do is we're going to write y1 and y2 and right-hand side. We're going to continue to write y's at the top until we have just one column left, and that far right column is going to be known as the right-hand side. Also, you're going to have a bunch of several rows. The last row would be the objective function, and all the rows that come before it, in this case there are 2 rows that come before it, will be the constraints, the ones with the inequality. Now, in the original problem, these constraints were greater than or equal to constraints, because they were constraints that you would typically see in a minimum problem. But the constraints over here in the dual are going to be the less than or equal to, because we're going to form the dual, which is a maximum problem. So here's the dual. And the fundamental theorem of the duality principle in linear programming says the solution to the original minimum, which is what we're looking for, is equal to the solution to the dual maximum. So we know how to solve maximum problems. So if we could just write a problem that involves, that it's in the format of a maximum problem, we can solve it, and then we'll reflect back on how we get the solution to the minimum problem. Okay, I'm going to write across an inequality. So the first 2 rows are constrained. So we're going to have 2y1 plus 3y2. The inequality symbol would be a less than or equal to, so we have a maximum problem, and then the number on the right-hand side is 12. In the second row, we have y1 plus y2, again, less than or equal to 5. And finally, the last one is it's a matrix of coefficients that corresponds to the maximum. And usually what we use for the objective function is p. So we're going to write 7y1 plus 9y2. We're going to add the non-negative constraints for these y's, just as we would for the x's. So all of this together, this is known as the dual. And it comes from this transposed matrix. Now, we know how to solve problems like this because we did it in section 6.2. So what we're going to do is we're going to solve this problem. We're going to dump it into the simplex program, enter in the initial simplex tableau, get out the output, which is the final simplex tableau, and then I'm going to show you how you interpret a matrix if you're looking for the minimum. Okay, so we've introduced 3 new variables here, y1, y2, and p. That wasn't in the original problem. The only 3 variables in the original problem are c, x1, and x2. So when you're done, you want to say, and since we're minimizing, you want to say the min is c equals this number, and it occurs when x1 equals this number and x2 equals this number. So just as before, you've got two variables in here, two decision variables they call them, and then you've got this thing we're trying to minimize. So we want to know what the minimum is and where it occurs. So we need to talk about then, well, what about all these other variables, these y's and these x's and so on. All right, what I do next, I'm going to go through this a little fast because I know that you've done this lots of times. So I don't want to take a whole lot of time, but remember we have to convert each inequality to a slack equation. Now, some of you are probably really good at this now, just taking this matrix and dumping it in and getting your final matrix or your initial matrix. But I'll go through the process of writing the slack equations here. If 2y1 plus 3y2 is less than 12, then we can add a non-negative number for which 2y1 plus 3y2 plus that positive number is equal to 12. In the next constraint, y1 plus y2 is less than 5, so if we add something to it, it'll bring it up equal to 5. S2 is also non-negative. And then for the objective, we bring over the 7y1, so it becomes negative 7y1. We bring over, using algebra, the 9y2, and then over with the p, it's written as negative 9y2. And if we bring both those terms over to the left, there's nothing left there except 0. All right, and then the next step is to form the initial simplex tableau. In this maximum problem now, we have the variables y1 and y2. We have two slack variables. They come next, s1 and s2. And the only other variable in this whole problem is the objective function, objective variable. And remember, we're going to reserve our final right column for the right-hand side. We have two constraints and one objective function. So you can expect to see 3 rows here. And the last row will always be the objective function. So picking out the coefficients of the first equation, I have 2 and 3 and 1 S1. There is no S2, there is no P, and on the right-hand side we have 12. The second slack equation, we have 1y1 plus 1y2. We do have a 1s2, that's here, but we don't have an s1 and we don't have a p variable in that second equation. And the right-hand side is 5. In the bottom row, it's important that you put the objective function in the bottom row, because if there's still negatives down there, well, negatives in the, see, we're taking p and we're subtracting something from it. So this is negative 7, negative 9. There's no slack because p started out as an equation, so we didn't need to add another slack equation for the equation there. That's 1p1. Some of you were missing this guy, so make sure you put 1p1 there. And then 0 on the right-hand side. And this one will always be 0 when you set this problem up. Okay, so this is the initial simplex tableau. We're going to run program simplex, and it's going to return for us the final simplex tableau. And once we get this final simplex tableau, then I will show you how to interpret it. That is, you know how to interpret most of it, but all right, so this final simplex tableau will also have y1, y2, s1, s2, p, and the right-hand side. Still have 3 rows. Just going to use elementary row operations to change some of these. And so I'm now going to pull out the calculator and enter in the initial simplex tableau. First thing I'll do is go enter in this matrix. I always just put the matrix into matrix A. And the first thing we have to establish when we're entering a matrix is the dimensions. So we have 3 rows and 1, 2, 3, 4, 5, 6 columns. So 3, enter, 6, enter. And then we want to enter in all of these numbers. So 2, I guess I did this already. 3, 1, 0, 0, and 12. 1, 1, 0, 1, 0, 5. And in the last row, -7, -9, 0, 0, 1, and finally 0. Okay, so get that initial simplex Tableau in there, and then quit. Right there above mode is quit, so second mode takes you back to the home screen. If you want to see your matrix, you can do that. You can kind of look at it. Just type A to the home screen, and you can make sure you've got everything typed in correctly. All right, so now we want to change this matrix to a form where we can see the solution. And to do that, we have to enter the program. So here's the program. This is where you put your simplex program in program. So I'm going to hit that. I've got a lot of programs. You may only have one. So we're going to scroll down to see simplex. Right there it is. I'm going to hit enter. Okay, now when I hit enter, it takes the program. Notice it says program simplex, all one word, and it throws it to the screen. Now it's not going to act until you execute the program, and you execute the program by hitting enter. So now I'm going to hit enter, and it's going to ask for the initial simplex Tableau. Now I don't want to re-enter that matrix here with a bunch of square brackets. I just entered it into matrix A, so I'm going to go recall my matrix A. It's in the matrix menu, and there it is, number 1. And then next to the prompt there, the question mark prompt, you're just going to see matrix A. And now it's just a matter of hitting enter until the program stops. All right, you can still see that because there's some fluttering going up here on these pixels, that this means the program is waiting for you to hit enter again. But it does say final simplex matrix. There it is. Looks like we've got some rounding error going on here. But before you hit enter, write down this matrix, because if you hit enter now, you won't be able to scroll to the right to see the whole thing. All right, so 0, 1, 0. I know there's only 3 rows. 1, 0, 0. And then we have 1, -1, 2. And I think just because of rounding error, this is going to be a -2, 3, 3. And then I need to scroll over. And you can see there's some rounding error at the end. And then 0, 0, 1. And then finally, I'm going to call this. This is 1.9999. You're going to see this rounding issues. I got to believe that that's 2. I got to believe that that next one is 3. And then we have 39. So ignore if something looks like it rounds pretty quickly to a whole number, then you probably want to do it that way. Or if you get a bunch of zeros like this or a bunch of 9s, definitely round it. Okay, now the first thing we're going to do is we're going to interpret this in the same exact way that we interpreted the maximum problems. So I'm going to start off with these non-basic variables over here. Scroll over till I see a 1 and zeros everywhere else. These 2 are 1s, but this one has a bunch of non-zeros with it. This is the only one that has zeros with it. Since the 1 is here, we go up to the top, see y2, and that's declared the non-basic variable of the first row. Replicate that for the next row. There's only 1, 1, and there's zeros everywhere with it. So y1 is the variable, the non-basic variable of the second row. And then if you go to the third row, there's your 1, zeros everywhere else, so P. All right, so in this matrix then, the basic variables are everything else. We have our y1 accounted for, we have our y2 accounted for, we have the P accounted for, but we don't have the S1 and the S2. And we always assign the S1 and the S2 zeros. And I'm going to come over here and, well, maybe I won't. Y2, its value is all the way over here, 2. Y1, its value is way over here underneath the right-hand side. It's equal to 3. And P is the non-basic variable. To get its value, go all the way to the right-hand side. Okay, now when you look at the values of all these variables, you're not very satisfied at all because not a single value that you need is listed. We're looking for C. What's the minimum of C? And it occurs at x1 and x2, and we have no x1 and x2 or value of C listed in this matrix. All right, so this is the one additional step in interpreting the matrix that I have to show you. And we need to find x1, x2, and C. C is the easiest one. C is going to be equal to P. So whatever the P value is, C is going to take the same value. This is the duality principle. The solution of the minimum problem will be the same as the solution of the dual maximum problem. And the solution to the dual maximum problem is P equals 39. So C equals 39 is the minimum value that we're looking for. Okay, x1 and x2 are the last two that we need. And it turns out that those values will be found in the last row corresponding to the slack variables. So S1 is here, so the value of x1 is in the last row underneath S1. And the value of x2 is going to be in the bottom row underneath S2. So x1 and x2 and C are actually in this matrix. You just need to know how to interpret the matrix. So S1 is there, x1 is 2, and S2 is equal to 3, and then here's your final solution. The minimum is 39, and it occurs when x is equal to 2, or x1 is equal to 2, and x2 is equal to 3. So this is the whole process. This is the whole problem. It's a little bit more involved. It does use the simplex method. And there are lots of variations on this. All right, so we normally could solve this problem, right? This one here, because it was a minimum problem and it involved just two variables. So we could solve it graphically. By the way, you might want to just take a peek at your constraints and at your objective functions just to make sure everything works out. For example, if I put 2 in there for x1, x1 is 2, and I put 3 in there for x2, 2 times x1 is 2 times 2, that's 4, plus 3, hits 7 perfectly. So it's greater than or equal to 7 is true. Here, if you take these two values for x1 and x2 and plug them in for x1 and x2 here, 3 times 2 is 6, plus 3 is 9. 9 is greater than or equal to 9. The second inequality is satisfied. And you know you're really close if you get 7 and 9 right on the nose like we did here. And then to get that 39, just take the 12 times the x1, 2. 12 times 2 is 24. 5 times 3 is 15. 24 and 15 add up to the 39. So it doesn't hurt to just kind of check to make sure that you've got the right thing. All right, so the different homework exercises that you have will do different pieces of this. And just for practice, why don't you tell me what the values of x1, x2, and C are? I guess the way I would do the way I would do it is I would put S1 here and S2 here. I understand why they put x1 and x2 there. So go ahead and write the values of x1, x2, and C. Okay, so this is the original minimum problem. When we do the transpose and write the new system, this is called the dual. It is a maximum problem. They didn't give you the initial simplex tableau here. They just said they took this, dumped it into simplex, and now this is the final simplex tableau. You know that it's the final Simplex Tableau, because when you look in the last row, you see no negatives. So in the chat, write the three values in this order, x1, x2, see, three values. If you don't know, question mark. All right, so it looks like we may have lost two people. Okay, yeah, very good. Everybody has it correct. This would be the P, and then this would be y1 and y2. So you could write down the values of all the variables, but the one you need is that P is equal to 155 and P is equal to C. And then x1 is 5 and x2 is 3. Okay. So if you encounter a word problem like this, then you have all the work that we just did for the previous problem, but you also have to generate the correct linear programming problem, convert all these words into a minimum problem. So you need the objective function, which is what you're trying to minimize, and you need several constraints. Could be one constraint, could be two, could be three, could be more. All right, so let's take a look at this one, and maybe I'll try to do it all right here. Regular and deluxe ice cream at 3 plants. So 3 plants, 2 kinds of ice cream. Per hour of operation, the Cedarburg plant, so it gives you information about one of the plants, 20 gallons of ice cream, 10 gallons of deluxe, 20, all right, so of each. The Grafton plant produces 10 gallons of regular and 20 gallons of deluxe. And then it gives the West. So 3 different plants. And here comes the cost. This is probably what you're trying to minimize. The cost is 70 per hours in Cedarburg, 75 in Grafton, and 90 in West. The company needs to produce at least. At least is the phrase that we use for greater than or equal to, at least. 30 gallons of regular, 20 gallons of deluxe. And then the question says, how many hours per day should each plant operate in order to produce the required amount of ice cream and minimize the production costs? And then what is the minimum cost? All right, my strategy for doing these word problems is to come down here and ask, what are they trying to find? We know that we're trying to minimize the cost, but how many hours per day should each plant operate? Since that's what we're looking for, I'm going to define my variables, x1, as the number of hours each plant operates. So the number of hours operating of, and then I'll just take them in order, Cedarburg. And then x2 would be the number of hours operating of Grafton. And x3 would be equal to number of hours of West Bend. Now I should leave some room over here for the right-hand side. All right, so we have 2 kinds of ice cream, regular and deluxe. So this kind of creates like a little grid for you. The other thing is cost. So I'm going to create 3 rows as if I have, or even it might even be more. We'll see. 3 rows, we've got 2 constraints, and we have a cost function. So I'm going to read again. I'm going to start putting numbers in here. Okay, the plant Cedarburg produces 20 gallons. Grafton, all right, so let me see here. I'm going to put these numbers in here, but I have to make sure that the units are the same. So 20 hours or 20 gallons of regular and 10 gallons of deluxe. Grafton is 10 hours of 10 gallons of regular and 20 gallons of deluxe. And West is 20 gallons of regular and 20 gallons of deluxe. And then for cost, it's 70 hours for Cedarburg and 75 hours for Grafton and $90 per hour for West Bend. The company needs to produce at least 300 gallons of regular. So that's the total over here. So we have at least, so greater than or equal to 300 hours of the regular, and at least greater than or equal to 200 of deluxe each day. Okay, so this thing here says per hour of operation, the Cedarburg produces 20. So 20 for each hour. So 20 gallons of regular ice cream for each of the X1 hours. So you can kind of see how the constraints in the objective function is going to form in front of your eyes here. But this is 20 times X1 times X1 times X1. And then the second column deals with all these features related to Grafton. Per hour of operation, X2, X2, and X2. And then per hour over here at West Bend is X3, X3, and X3. This bottom one is the cost. So I'm going to say this is the objective function. There it is, cost. And then we have these two constraints. But X1 is the number of hours per day, so it has to be a non-negative number. So we are going to have these basic constraints as well in this problem. We're not going to go back in time and have a negative time hours per day. Okay, so there's all this work that you need to do in order to solve this problem. But let me write down this problem as a minimum problem, and we'll go through another one completely. Now this one's a little different because we wouldn't be able to solve this problem back in chapter 5 because it contains more than 2 variables. Our first problem contained only 2 variables. So let's see what this one looks like. We start with the matrix of coefficients, and I'll list the constraints first. So we've got an X1 and an X2 and an X3 and the right-hand side. The first constraint, 20, 10, 20, 300. The second constraint, related to the deluxe ice cream, 10, 20, 20, and 200. And then in the very last row, we ran out of constraints, so the last row is going to be the objective function. And remember, for this one, we're not getting everything to one side or anything like that. We're just going to write down the matrix of coefficients, 70, 75, 90, and then again, begin with 0 here, always. All right. X transpose. Each row becomes a column. First row becomes first column. Second row becomes second column. And the third row becomes the third column. And here's the transpose matrix. But because we transposed everything, we need to cut off the last row and cut off the last column, because we want the last column to be reserved for the right-hand side, and we want the last row to be reserved for the objective function. We're going to start labeling. The first row is Y1, and the second row is Y2, and then we run out of Ys. So that's it. So that's good. That's the simplex with the matrix. That's the transpose with the matrix labeled. All right, the next step. Now, let me just tell you, as you do these enough, you're going to be able to go from this matrix right to the initial simplex tableau. I'm going to at least today, I'm going to go through the details on this. All right, so take each row 20 times the variable in that column, y1, plus 10, y2. And then the original problem had greater than or equals to, but the dual will have less than or equal to. And then you've got the right-hand side 70. The next row, 10y1 plus 20y2 is less than or equal to 75. This one, since we have another row before we get to the objective function, that one, this third row is also a constraint. 20y1 plus 20y2 less than or equal to 90. Okay. And then finally, the objective is P, and we have 30 or 300 x1 plus 200 x2. We also know y1 greater than or equal to 0, y2 greater than or equal to 0. Just two variables in there. Now, if you just think about it, we have three constraints here. That means we're going to introduce three slack variables. And that's a good thing, because when we get our final simplex tableau, at the bottom of those three columns will be x1, x2, and x3. So the number of slack variables that you have in your dual will correspond to the number of variables in the original problem. All right, so since we have 1, 2, 3 original variables, we have to have 3 slack variables so that we have a final matrix that has 3 slack columns. And at the very bottom of the slack column is where we're going to find our solution. All right, so now we're going to go with the, well, I guess I'll do the slack equations first. Remember, this is what we would call the I system, and we want to convert it to an E system. So we have 20y1 plus 10y2 is less than or equal to 70. So if we add a slack variable, we get something equal to 70. The next row, 10y1 plus 20y2 plus s2 is equal to 75. And then the third constraint, we can't use the same S1 and S2 because the third slack variable might take on a different value than the first couple. So we have 3 slack variables. And then we're going to write P. We're going to bring over the 300 x1, so that's P minus 300x. We're also going to bring over the 200 x2. And if I bring both of these two algebraically over to the left, then there's nothing left on the right. So equals 0. Next step would be to write the initial simplex tableau. So the y's come first. We have y1 and y2, no other y's, just those two. Then we list the slack variables, s1, s2, and s3. Then we list the variable associated with our objective function, p. And then finally, the right-hand side. The right-hand side is a number. It's not attached to any variable. We have 3 slack equations in an objective function, so therefore we're going to have 4 rows in our tableau. The last row would be the objective functions row, and the first 3 would be our constraints. Okay, so 20y1, 10y2, 1s1. There's no s2 and no s3 and no p, and then we've got the 70. You will definitely see some shortcuts in setting these up when you do a bunch of them. Next one is 10, 20. There's no S1. There's an S1 or an S2 and no S3 and no P. The third constraint, 20, 20. There's no S1. There's no S2. And then there's a 1S3. There's no P in that equation. And then we have the number on the right-hand side. And finally, we have negative 300. Oops, these are y's down here. These should be y's. minus 200. There's no slack variables. Don't forget to put a 1 here. If you don't put a 1 here, you're not even going to have a p in the equation. Everything in here is going to be zeros. And then you're always going to start with a 0 there as well. So there's the initial simplex tableau. Lots of steps. We're going to do program simplex, and that's going to give us the final simplex tableau. Now, do you think you can do it? Can you skip a couple of steps? Do you see these coefficients here in the transpose? Do you see how they fall into the initial simplex tableau? 20, 10, 70, 20, 10, 70, 10, 20, 75, 10, 20, 75, 20, 20, 90, 20, 20, 90. These positive numbers become negative numbers. The other thing to look for is that you have the identity matrix right here. 1, 0, 0, 0, 1, 0, 0, 0, 1, and all zeros down here. So x1, x2, and x3 begin at 0. And after we do some elementary row operations, that's going to change a little bit. Okay, this is a 1, 2, 3, 4 rows. 1, 2, 3, 4, 5, 6, 7 columns. So this is a 4 by 7 column matrix. 4 rows, 7 columns. So I'm going to go enter the initial simplex tableau into the matrix. It's now 4 by 7. 4 rows, 7 columns. So much bigger numbers in an application like this. 10, 20, 0, 1, 0, 0, 75. And 20, 20, 0, 0, 1, 0, 90. And then come the negatives. Negative 300, negative 200, 0, 0, 0, 1, and then 0. And I can type my matrix to the home screen and make sure that everything is correct. A lot of times to get the incorrect answer, all it takes is just a single error. Okay, now I'm going to run program simplex. Okay, just remember that here is not where you enter in the matrix. You got to hit enter first, and then it's going to ask you for the initial simplex matrix. And that's when you're going to go back into the matrix menu, and while you're in the column with names, just select option number 1. Notice that now matrix A is 4 by 7, the one you just entered in there. All right, I'm going to hit enter to get this thing working. It's going to do all these row operations behind the scenes. All right, so this is not the final simplex matrix because it doesn't say final simplex matrix up at the top. You also see these pixels fluttering here, which means that you need to do another round of row operations. So hit enter, and then it comes up with the final matrix. So let's enter this one down here, and then we're going to interpret it. Oh, it's nice. It tries to put everything in fraction form, because if it's in fraction form, it doesn't take as much space on the screen of the calculator. Okay, so here's the final simplex tableau. I'm going to put the labeling on it. That is, I'll separate the constraints from the objective function. I'll also separate the variable pieces from the right-hand side. So we have y1, y2, s1, s2, s3, p. Okay, the quick way to read it would be to look under the s's. So look here. We have x1. Notice x is not even in this matrix. But you go to the bottom row underneath S1 to find X1. Go in the bottom row underneath S1 to find X2. And then go underneath S3, the bottom row, to find X3. And then this number over here is going to be your p-value. But the duality principle tells us that it's also going to be the solution of the maximum problem or the minimum problem. All right, so let's now go back and answer the question. They're saying that the minimum solution occurs when x1 is 10, x2 is 0, and x3 is 5. So coming back to this original problem, x1 was the number of hours per day working at the Cedarburg plant. Same for the others. So we should say that it says how many hours per day should each plant operate? So our answer is Cedarburg should operate x1, 10 hours per day. Looks like the people at Cedarburg are going to earn a little extra pay, a little overtime. The next one is Grafton, 0 hours per day. Do you want to know why plants get shut down? Linear programming problems. 0 hours at Grafton. And 5 hours per day at West Bend. If they change their hours in this way, the minimum cost would be, this is cost per day, is $1,150. So we're linking this problem back to our word problem and writing that final sentence.